My name is Travis Goodspeed, and today I'll be telling you how to build your own thumb drives. When you first learn how to program, and you learn how to write hello world and those other things, the one thing that you're often lacking is the ability to use sockets. And there's this revelation when you first learn how to open up a socket to a web server or as a web server, that the protocol is really easy. All you need to do in any telnet terminal is type in get/http/1.0 two returns, and the index page of the website will pop up. And there are a couple of complications on top of that, but not that many of them. And you don't need to be a god of programming to be able to write a web server. So what I'm going to show you today is that you can write a hard disk in the same way. You can use a regular scripting language, in my case Python, and cheap hardware in order to write your own thumb drive. And then having a disk that's connected to the computer, you can begin to attack that computer or to experiment with nifty tricks against forensics experts. It's traditional at the beginning of a lecture to begin with a plug for the employer. So this is the part where I'm supposed to get up and say, you should respect the professionality of IBM, or you should respect the professionals at HP, or whatever firm I worked for. So being self-employed, I figured I should make up fake companies to plug instead. So I would like to invite all of you to pay attention to my new fake startup company, which is aptfriendfinder.com. Because we all know that APT is really about blaming the Chinese. But we've had this problem that it takes weeks to blame the Chinese. So APT Friend Finder is a Perl script that will identify Chinese characters within any binary file, right? So let's take /bin/ls or Wireshark, for example. So we can run APT Friend Finder on Wireshark, and then we can see all of these Chinese characters and their definitions, which allows us to blame the Chinese in minutes instead of weeks. They're no more responsible. I mean, we're still just fabricating evidence here. But you can come up with APT names for any piece of malware that you have. So for example, we could call this rank owner sheep promise from the rows near the bottom, and that allows us to join in the APT. So back to the serious content. The hardware in the background here is a prototype of a device of mine called the Face Dancer. Excellent. The Face Dancer is a circuit board that allows you to write your own USB devices, and in more recent versions you can also implement a host. So this way your Python script becomes a disk or a keyboard or a printer. You can emulate a scanner, you can emulate a network card, you can emulate a serial port, and through emulating a serial port you can emulate all sorts of devices very easily. For example, an uninterruptible power supply is just a USB serial port with a specific vendor ID and product ID. So you can emulate that and then tell the host to reboot, and the host will do it because it trusts the battery to tell it what to do. So I'll begin by introducing the Face Dancer itself, which is a framework for allowing you to speak USB in the same way that you would speak TCP or UDP. So it's almost like a network card, but it's a network card for accessing the bus in a way that you're not normally supposed to. Because your laptop, in normal usage, can only be a host. Your phone can be a device, but those can be a bit tricky to program. So what this allows you to do is you plug it in by USB to any device, any laptop, and then that laptop can emulate any USB device that you like. I'll also be talking specifically about how to emulate USB mass storage and what interesting things you can do when you control mass storage. For example, Colin Mulliner has published a useful time of check to time of use vulnerability against a Samsung television. This allows him to very quickly introduce a backdoor giving him a telnet shell on the television. And he does it by abusing a shell script inside of the TV. The TV only allows you to install plugins that are .swf files. He wants to install a plugin that's a .so file where he can use native code to launch a shell. So inside of the TV, there's a shell script, and the shell script begins by saying, if this plugin is safe, then install it. During the if clause, the file is read for the first time, and it's a safe file. It's a .swf file. If there was signature checking, it would have a valid signature. The second time is the time that it's actually installed, and it's at that point that he swaps it out for his malicious file that drops the shell. And all he needed to do was to hook the request of a single logical block address. He did this using a Nokia N900. Using the face dancer, you can do it with a lot less hardware and a lot less expense. So other reasons for implementing USB include kernel ponage. You know how Linux supports every USB device ever manufactured except for the wireless card in your laptop? Well, those are all, it's true. Those are all open ports speaking complicated protocols. If you ran Nmap on a server and you saw that it had 500 ports open, most of which were never used, you would know that there was a memory corruption exploit somewhere, or vulnerability somewhere. Well, with Face Dancer, you can begin fuzzing those device drivers. So you can start scanning a USB to serial driver, or a USB mass storage driver, or a file system driver. There are all sorts of pieces of the code that you can reach by running through the USB port externally. Once weaponized, you can have a little thumb drive or a little old-fashioned iPod that you plug into a machine, and it drops a root shell. For forensics, you can use this both in favor of or against forensics. So on the defensive side, you can start talking directly to a disk without having an OS between you and the disk, which means that you can start doing things like making requests to dump weird regions. You might be able to dump the scratch sectors of a disk that are not mapped into the image as shown to the host. Every hard disk has large regions that are used for its own record keeping. I was taking apart a Seagate hard disk that had a 500 megabyte partition that was never exposed to the host operating system, because this is where the disk contained its own logs. Well, by reading those logs out, you can try and figure out whether the disk has been wiped recently, or whether it's legitimately blank. You can also work on the other end, and you can start developing techniques to make an anti-forensics disk that will destroy itself if it's being forensically analyzed. The very first thing that Windows does when it talks to a new disk is it writes a timestamp to it. The one rule of forensic science that you're never allowed to break is that you're never allowed to write to the disk, because that's tampering with evidence. So from that one little check, is the timestamp written or is it not written? Well, that lets you know whether you're in a forensics lab. You can also check to see whether the disk is being read sequentially or if the file system is being followed. When a legitimate machine mounts a disk, it follows the file system as a tree. So it will go down the directories as they're accessed. If it has an indexing service, as Macs do, it will begin running through every single directory just for the hell of it. But in a forensics lab, they begin at sector 0 and they work their way all the way up to the end. So if you see the disk being read sequentially at the beginning, then you can destroy the disk contents toward the end. But developing these techniques requires a development kit, because writing code that runs inside of a hard disk, inside of a physical commercial hard disk, is rather difficult. Writing Python code that runs in your host is very easy, and that's where the face dancer comes in. You can also build things like fake video game controllers. So if you start rewiring, let's say you have a PlayStation controller that you like and you want to use it with your Xbox. Well, your Xbox won't allow you to do that because it has a lockout chip. By implementing your own USB devices, you can sort of forward the lockout chip from the Xbox controller and combine it with the input from the PlayStation controller, and your Xbox won't know the difference. You can fuzz one machine from another machine using this framework. On the left, we have a MacBook Air, and on the right, we have a MacBook Pro. The MacBook Air is fuzzing the human interface device descriptor tables. This is a very small piece of USB, and it's one that's not often It's not often thought of as being a device vulnerability. You think of this, as being an application vulnerability. You think of this as being a kernel vulnerability. Now, Apple, unfortunately, has checked for this. So they've cleaned up their HID drivers and have not been able to get any crashes from the HID descriptor tables. But these bugs are everywhere. Here, the fuzzer is crashing the video card driver in Linux. Here, fuzzing HID on Mac, and remember that OS X itself does not have HID vulnerabilities. Skype does. So Skype here is crashing because I'm presenting it with a weird keyboard. This is because Skype starts looking at all of your USB devices in order to figure out whether you have a USB headset. And they didn't bulletproof their code in the same way that the operating system did. I've also found vulnerabilities this way in utilities that you would expect to be bulletproofed. LSUSB would crash for a while if you didn't send it some of the results that it expected. There are memory leaks in that if you send not enough information, the host will leave kernel pool memory in that place. So you can use this to spy on what other users are doing within your system. This is our initial prototype. Up here on the top, you can see one of my Goodfoot boards. This is just a USB to serial chip and a microcontroller. And all the microcontroller does is expose the port that's after it to the host. The thing that's after it is this larger green board, which is a Maxon development kit. When you want to work with a microchip, the vendor wants to help you out, because if you design a product with that chip, you might sell thousands or millions of units. So you can buy these development kits that contain the chip that they want you to learn how to program, along with some example software, all neatly wired up so that you can easily wire into it. So I wired into it, and at this point I had Python access to the Max 3421 chip, which can do both USB host and USB device. At this point, I'm doing USB host to a Wi-Fi card. And that Wi-Fi card has a minor vulnerability in it, which is that there's a string of names. If you're using the Russian version of Windows, and you plug in a device, you see its name. If that device is intended for a Russian market, it will include both the English name and the Russian name. In order to choose between these, it has a descriptor table that describes which languages it lists. And each one of these has an index into a string table. So 1 might be the English name of the manufacturer, and 2 might be the Russian name of the manufacturer. And 3 might be the Russian name of the device, and 4 might be the English name of the device. On many devices, I've found that you can walk off the end of this descriptor table. So when implemented as a C array of string arrays, you can just walk right off the end, and then whatever value is after that in the initial array of pointers, well, it will jump to that address, read the string, and return it. This allows you to grab pieces of memory that don't belong to you. And in many cases, you can use this in order to dump a password out from the end of memory. A lot of these chips will not reveal their firmware unless you know the interrupt vector table or some other password that's held within memory. So by dumping out memory, you can find that table and then feed it back in as if you knew the password all along. The new hardware, as shown here, is a standalone board. I have these manufactured in China, and I distribute these through Tennessee. This is a hobby project, so we send them out for free to students, or for people who do have money, we only charge for shipping. Whatever excess you send in shipping goes to ship these to students, so the students don't even have to pay for shipping when they get them. The left side of the board connects to your workstation. There's a mini USB plug which connects to your laptop. Then this chip here, with the 2 rows of pins, that's the FTDI232RL chip. And this chip only implements USB to serial. So as far as the host computer is concerned, you get a new COM port, or you get a new /dev/TTY USB 0 port. When you talk through that port, you see the MSP430 chip here. This is the MSP430 2618. And this chip runs a very small C kernel whose job it is to forward traffic between the USB to serial chip and the standalone USB chip, which is this one on the far right here. This is the MAX3421. And the purpose of this chip is to allow you to implement a USB device. This was popular several years back with MP3 players. If you remember when they first came out and you would have a device that was just your MP3 player and wouldn't play movies or anything like that, they would use a USB chip of this class. And the nifty thing about this chip is that they assumed that your MP3 player design would not be fast enough to speak USB properly. That you would need to use most of your processing power for audio. So what they did was, they have this Maxim chip handle all of the tricky timing requirements of USB. So USB often requires that a host or a device will reply within 50 milliseconds. Rather than having to do that through a round trip to the host, where you might not have enough time, the Maxim chip does it for you. And it's like a secretary pretending that the boss is busy. Whenever the host hasn't given it new information yet, it just tells the host on the other side to back off for a minute. And in doing this, it's able to stall long enough that the host on the right side of the board never knows that the thing on the left side of the board is terribly slow. So these, again, are the three chips. You have an MSP430, which runs a small piece of firmware. You have an FTDI chip, which connects the MSP430 to the developer's workstation. And you have a Maxim USB chip, which connects the USB host to the victim. Now, while we distribute the boards freely, we don't have time or the budget to assemble them. So when you get this board, you need to either assemble it or you need to bribe a student to assemble it for you. The soldering for this board is not terribly difficult. I've taught people who had no prior experience in surface mount soldering to build these within a week. The trick is just to tack a pin on one side and then to rotate the chip around that until it's in the proper position, and to use lots of flux. Now, the software in this does as little as possible on the C end, because the purpose of the C end is just to shuffle communications between the host and the USB chip, the developer's workstation, the USB chip. In doing this, it's just exposing that chip to the host. So in order to develop for this, you take the development manual for the Maxim 3421 chip, and it will tell you to load something into a register. You will have a Python command to do that. So you're implementing it in Python on your workstation in the same way that you would be implementing it in C on a microcontroller, except that you have gigabytes of RAM, you have tons of disk storage, and you have lots of debugging feedback. Having a working debugger drastically simplifies this. We then moved as much of the complexity as possible into the Python firmware. We did this so well that later on, when a clone of this was made called the Raspberry Dancer, that's based on the Raspberry Pi, when this was being made, it only took a single page of Python code to allow our Face Dancer software framework to communicate with the Raspberry Pi's SPI port and the Maxim chip on the Raspberry Pi, rather than Face Dancer board. And this is drastically different hardware, but the software was able to remain compatible because everything that you're coding in Python is actually for the Maxim 3420, and almost none of it is for the MSP430 or for the higher levels. Here's an example of the code. You'll notice that it's almost all hex. And all that this code does is return that block of hex. This function is called getSectorData, And in order to implement a disk, all you have to do is subclass 3 of these functions. You subclass get sector data in order to allow reads from the disk, put sector data in order to allow writes to the disk, and get sector count because the host needs to know how many sectors physically exist within the device. Now, once you've done this and you connect it up to the target, you can then read and write this disk just like you would any other disk. Here I'm using DD in order to read the first block of it and then dump that out as hexadecimal. And it reads these 512 bytes just as if this were a regular disk. The host has no idea that this disk is fake. And you can even mount it. All of your GUIs will work. You can explore it in file managers just as you normally would. Here I have the disk from FreeDOS, which is a free clone of the DOS operating system. And you can see here that it's mounted by USB in a KDE environment, and the host doesn't know that it's special. This is a picture of the MAX 3420 chip. And this is what's doing all of the legwork. So whenever you want to do anything fancy at the low levels, you just look up the documentation for the MAX 3420 chip. Whenever you want to do anything at the higher levels, instead you look up the documentation for the USB standard that you're implementing. USB mass storage is implemented as a wrapper around SCSI. So when you're trying to implement a USB disk, you get 17 pages of documentation, 15 of which are committee nonsense that tell you nothing. And eventually you realize that the reason why the standard doesn't tell you anything useful is that it's just telling you to embed SCSI inside of a wrapper. So if you remember when you first wrote a web server by opening up that socket to a host, and you first realized that a GET query was the only thing that you needed to fetch a page, or that supporting a GET query was the only thing that you needed to deliver a page. Well, the same thing happens with USB. As soon as you realize that the USB mass storage specification is only wrapping SCSI, then you realize that implementing SCSI is the only thing that you need to do. And SCSI has been around forever, and it's a rather easy language. It's not quite so easy that you can do it in ASCII. But it's close. So these sockets being different than TCP or UDP, your laptop doesn't have the hardware. That's where the face dancer comes in. Once you have the hardware and you begin implementing these protocols, you see that they're done in terms of datagram packets, sort of like UDP, except that unlike UDP, they will never be rearranged on you. In UDP, you have this worry that if you send two packets over a long distance, they might arrive in the opposite order, or one might be dropped without the sender being informed. USB doesn't have those features, but what it does have is that the divisions between packets matter. The individual packets are not scrunched together into a text stream as TCP is. You have these things called endpoints, which are sort of like ports. But they're ports in the software developer's view of things, not in the system administrator's view of things. By this I mean that if you look at a port on a host and you see that it's 21 or 22, that tells you what the service is. This is by custom, not by necessity. On a USB device, your endpoints are controlled by what the hardware offers. So you have endpoints like 1 or 2 or 3. And they don't really imply a protocol. In order to figure out the protocol that's being spoken, there's a special endpoint called EP0, or endpoint 0. And endpoint 0 is used to configure the device. When you have a host, until very recently, you didn't have any way to automatically configure it. With a USB device, from the very beginning, they realized that you would plug this into a host, and it should set itself up, and it shouldn't bug the user for that much. You shouldn't have to tell it which port means what. You shouldn't have to edit any text files. So the way they implement that is by sending these tables called descriptors over endpoint 0. This is the setup endpoint, and it's the only endpoint that works in both directions. Now, you also have an address for the device, which is a single byte. 0 is the device that the host has when you first power it on, and it's also the address that the device will go back to if it crashes. Now, if you're trying to fuzz a USB device for vulnerabilities, this is very important, because this allows you to know when you have crashed the device. And the most important thing when fuzzing is to know which input triggered the crash that might demonstrate your vulnerability. So by looking for the device at address 0 always, and recognizing that whenever it changes from the assigned address back to address 0, that is a crash, you can then identify when a device has crashed and then come up with exploits that will rewrite the firmware of a device. Now, the hosts and the devices are fundamentally different in that the host always initiates communication, and the device only speaks when it's spoken to. So the host will poll the device for data whenever it feels like it. It's required to poll so often so that the device knows that the host is alive. And devices only reply to this polling. A device can't speak out of turn. Something like well-behaved children. In the States, we say that children should speak when spoken to, and they don't. But this timing can be awkward because the hosts have to poll regularly. If they don't poll regularly, the device will see that something is wrong, and it will give up. And the devices have to reply to this polling even if they're not ready to do it. The way that this works is that the device sends either an acknowledgement or a non-acknowledgement, and it sends this in response to every single poll. But the CPU of the device can't be bothered that often. So what they do instead is they move this acknowledge or non-acknowledge feature into the Maxim chip. And this prevents round-trip times from stopping the face dancer from working. If it weren't for this feature of the Maxim chip, the design would be drastically more complicated because we would have to implement this polling acknowledgement ourselves. Now, USB mass storage is a thin wrapper around SCSI, and SCSI isn't very hard, especially in the USB dialects, because most operating systems have reduced the number of SCSI commands that they expect the device to understand. When you look at the SCSI documentation, you'll see these numbers inside of a parenthesis just after the read or write commands. So the most common ones for USB are read 10 or write 10. This refers to the size of the logical block address. So you have read 6 in very old devices. But when you wind up with disks that are many gigabytes in size, then 6 bytes of address space are no longer enough. So you have to extend it to 10. After 10, there's support for 14 bytes of address space. This allows you to have devices that are very large, and they did this for forward compatibility reasons. These were added to the standard in the 80s before devices of such large sizes existed. It's also important to realize that a USB device implementing mass storage will reboot whenever there's an error. And this isn't necessarily a crash. It will reboot on an error in order to resynchronize communication with the host. In SCSI, you use dead reckoning, which is where you count the number of bytes in the transaction, and you might have a lot of them. And the transaction doesn't end until that many bytes have been sent across. If you become desynchronized, then the host and the device can't agree on where they are. So they might treat metadata, that's the command, as data, which would be the thing that you're reading or writing. And this can cause all sorts of hassles unless it's fixed. And there's no safe way to fix it without ending the present conversation and demanding that the host start a new one. So the device will stop replying to anything until the host reinitializes it. And as a device, you have to support this. because the host will expect you to. Now, SCSI reads and writes are done in terms of logical block addresses. And these are done in terms of 512 bytes. So address 0 in SCSI is the first 512 bytes of the disk. That's the first sector. Address 1 is the second 512 bytes. There is no way to address anything smaller than a block. So you can't read a byte at a time, you have to read a block at a time. It's also the case that some special disks have different block sizes. This isn't always properly supported by the host operating system. So as a sort of convenient standard, everyone has stuck to 512 bytes, because that's what MS-DOS used for floppy disks. In recent times, there's been a movement toward either 8 kilobyte blocks or 4 kilobyte blocks in order to match the block sizes of the file systems that sit on top of these disks. It's rather rare to see Linux request only a single block from inside of a file system, because it always loads them in larger chunks for its own benefit and its own performance. You also have SCSI descriptors that describe how the disk works and what it can do. We think of all disks being the same because all hard disks and thumb drives behave kind of similarly. But at the time that the standard was being written, that was not the case. You had things like zip disks and CD-ROM drives that could be ejected. And the host needs to know that the disk supports this, because it needs to know whether or not you should be able to eject the disk in the way you would a CD-ROM. It needs to know whether the disk can be written, because there's no sense in doing a random write to a CD-ROM drive. Even writable CD-ROM drives require special commands because they have to be written in order and as the disk is spinning and without any pauses. You also need to know the cache policies of the disk. The host needs to be able to speak to the disk and to tell it to flush its cache. For example, after you write the metadata for the disk, say you rewrite the journal of an ext3 partition, you need to order the disk to flush that out so that the disk isn't damaged by being powered down at that critical moment. At the same time, if you're writing a random file later on that's only used for temporary purposes, there's no reason to flush that out to the disk. So everything in the temporary directory can be kept in cache. And at the time that the standard was being written, the cache that's physically in the disk was among the only cache that you had. This was before the operating system's file system cache became the dominant cache for performance. Now, in Linux, the disk will appear on a regular SCSI bus. So you can speak to it like you would any other weird SCSI device, including tape drives and scanners. If you want to implement your own devices, or if you want to emulate a strange device that you can't find physically but still want to write a userland application for, this will allow you to do it. And you don't need to know very many SCSI verbs. In my disk implementation, I only use these verbs. So 00 checks to make sure that the disk is ready. And you have to reply to this, but you just send an OK back. 03 checks to make sure that the disk is physically loaded into a removable drive. And again, you just say, yeah, it is. 12 is used to check the capacity of the disk. And it's used to check that it's writable, and it's used to check whether it's ejectable. This is rather complicated to implement because there are checksums for each of these tables, and the table formats are rather strangely documented. After you get that working, you only need to implement the read and write sector commands and the command to eject the disk, because some operating systems will send this whether or not the disk is ejectable when you close it. And that gives you a disk. And this disk is readable, it's writable, and it's also tamperable. So you can start playing around with it to add strange features that don't exist in any real-world disks. What Colin Mulliner did with this was he implemented a time of check to time of use attack against a Samsung television. The idea is that there's a shell script somewhere in the television that says, if the plugin is legal, then install it. And what he did was he swapped it out under the hood by having the first time the file is read present a legal.swf file inside of the XML wrapper. So at this point, the television believes that the file being installed is safe to install. Then he flushes the disk cache, and he does this by making the file very large so that the file system cache doesn't remember the beginning of it. So when the second shell script reads the file again, it reads it a second time. It physically hits the disk and does not read it from file system cache. And at this point, he presents an illegal plugin. But this plugin, while it's illegal to install, is legal to run. So the shell script will accidentally install it because it implicitly assumes that the file will not change when it's not being looked at. This drops a shell on the television, and since everything runs as root, he's now able to do anything with the TV that he would like. You can also prototype stranger things. I played around with active disk anti-forensics. The idea here is that disks can tell that they're being imaged in the same way that a web server can tell that it's being crawled. So you can respond by self-destructing, which a web server can't, because a web server has to maintain uptime. So a web server can blacklist a user, but it can't actually destroy the contents of the disk. An active disk can. You also have these easy ways to fingerprint what the host is doing. So forensics labs will never write to the disk, and they read from the beginning to the end. Windows behaves exactly in the opposite manner. It first writes a timestamp when mounting a volume. And then after writing that timestamp, it dances along the file system structure. So if you see sequential reads from the beginning of the disk to the end, then you know that the host is suspicious, and you should destroy the contents of the disk. There are other uses for fingerprinting hosts. There's a device called the ISO stick, which is intended for system administrators to install their own CD-ROM images by .iso files. And rather than having to burn them to a physical CD or to image them directly onto the thumb drive, what they do is they just write them in as a file, and they write as many as they like. So you can copy in 5 different files, all of them .isos, and whenever the ISO stick sees a Windows or a Linux host, then it's a writable thumb drive. Whenever it sees BIOS, it's a bootable CD-ROM with a very small kernel that allows you to choose which of the ISO images you want to load, and then it bounces to that as a second stage bootloader. And it can do this because different hosts speak wildly different dialects of USB and of SCSI. So Windows sort of stutters when it reboots. So it requests block 0 several times. I think it's 8 or 9 times, because at no point do they cache block accesses. In Windows, they only cache file system accesses. Linux has auto mounters even if you think you don't have auto mounters. So when I plug a mass storage device into my Debian Linux machine, even though I don't have an auto mounter enabled, the kernel will still follow the file system structure in order to see what file system that partition is. And you can watch this on the kernel logs through the face dancer. Now, a Macintosh will use sophisticated and old-fashioned USB words that no one uses these days. And if you don't implement them, then your device won't work on Mac while it will work on Windows and Linux as an accidental bug. To use this, you just have the GoodFet Max USB Mask class. This is available from the website that I'll have at the end. You then grab a sector by its logical block address, and you write a sector by its logical block address. And there's a function to get the sector count. So you subclass just these 3 functions, and then you have a disk that you control. There's an example that you can run which presents any given file as being a disk. So you run goodfet.maxusbmask on a .iso image, and that ISO image appears to the second machine. To move to standalone hardware, there are USB programming examples for the iPod, or for a couple of other devices which have been reverse engineered. If you actually wanted to do USB anti-forensics in the field, like as a secret disk that couldn't be read by forensics experts, what you would do is you would take an iPod or a Hello Kitty thumb drive or something that wouldn't look suspicious, and then you would reflash it with a new kernel to implement these techniques after you developed them with the face dancer. So the face dancer is a tool for development and not for deployment. If you wanted to attack an anti-forensics disk, there are exploits that you could use, and there are vulnerabilities that could be attacked. You could read the memory chips directly. You can also look for a ROM bootloader in the disk in order to dump the contents directly. But all of these attacks are slow, and they're all expensive. So if these disks ever became common, it would be very inconvenient for forensics analysts, because every time they imaged a disk, they would run the risk of destroying the contents. So the end result is that even if it were possible to break around these anti-forensics features, which certainly it would be too expensive to do on a regular basis. And you could only afford to do it when there's particular suspicion that an anti-forensics disk were in use. The face dancer has also been released as other designs. So this one is for the Hacker Conference badge from NoSuchCon. It can be assembled in the same way. If you want to use this design yourself, it's BSD licensed and completely open. You can take the Gerber file, slap some artwork onto it, and have a board of your own. So I have a few Face Dancer 11 boards with me to give away today. The code and the hardware designs can be grabbed from the SourceForge website. They're all in a Subversion repository. And I have articles on how this works that I've written at travisgoodspeed.blogspot.com. So at this point, I'd like to ask if there are any questions. Great. Thank you kindly for your time and attention. If you'd like a face dancer board, catch me after the lecture.